So last time we discussed the issue of cracking of concrete, and then we said concrete is going to start to crack once the tensile stress at the bottom, which means at the tension side of the beam, is going to be approaching this value FCR of 7.5 square root of F prime C. And if you see F prime C in any of the code equations, you need to use it in psi. You cannot really use it in ksi. We discussed this issue. We said what happened if I use it as 4k psi, just use the term 4 here, and then try to divide that in by 1,000 versus the use of just 4,000 psi. And we find out that there's a big difference here. It's going to be 474 psi versus 15k psi. So there is no way that the concrete is going to be much stronger than that, than the same material in compression. So for example, compression is going to be 4k psi, and tension is going to be 15. Doesn't make any sense. Therefore, I realize that I've done a mistake by just using 4k psi in this equation. Now, if you have been asking here to find out the cracking moment. Now, what is the cracking moment? I understand the cracking stress. The cracking stress is going to be the stress at the bottom of the beam, which means at the tension side in this case, at which the beam is going to start to crack. So what is the cracking moment? The cracking moment is going to be that moment at which the stresses is going to be approaching this value here, 7.5 square root of prime C. Therefore, you're going to start here to load the beam. And you're going to be increasing the load. It's going to be like incremental loading. Now, once the stress here is going to be reaching in the tension side, is going to be reaching this value here, let's say for 4,000 psi concrete, 4,000 psi is going to be 474. So once the stress is at the bottom of the tension side is going to be reaching the 474 psi, we say now concrete started to crack. So, and the other question is, so what? What's going to happen? Well, it depends. If you have no reinforcing, it means the beam is gone. The beam has no value at all if there is no reinforcing. Where at reinforcing, usually we put it at the tension side, which means at the bottom of the beam. This is going to be number one issue. If you have reinforcing bars, this is great because now once the beam is going to start to crack, your beam is going to survive because now this rebars is going to start to support loads like tension force. Meaning, before the cracking point, the reinforcing bars are doing nothing. The performance of unreinforcing beam is going to be the same as reinforced beam if the amount of load and the moment is lower than the cracking moment. Let me repeat this. Now I have two beams. One of them, you can say here, it has some reinforcing, like this beam. Other one is very similar to it, same dimensions, same concrete material, but has no reinforcing. Between the 0 point loading and between the cracking moment, both beams would perform exactly the same. There's no big difference. So the rebars are not doing anything as long as the applied moment, which means the moment that you apply to the beam is lower than the cracking moment. So just to confirm again, if I have two identical beams and the difference is only the reinforcing, between the point of 0 loading and between the cracking moment, both beams would perform the same. There's no big difference between the two. Also, we discussed this issue about the stress distribution due to flexural loading. Flexural loading means moment. Once I say a flexural loading, it doesn't mean axial load, it doesn't mean like shear, it means a moment applied on the beam. Once you start here to apply a moment, this is going to be your stress distribution. You're going to have tension at the bottom and compression on the top. If you can do here integration of the stress block, this triangular block, you do integration, you determine the force. I can give you here a simple example. Let's go back here to axially loaded members. If I have a rebar exposed to tension force, you take this tension force, you divide it by the cross-section area of the rebar. It's going to get you a stress. Now, this stress value, if you imagine, is going to be like one of these blocks or one of these stress blocks, stress distribution. And if you draw it in a way like this, or in a way like, I'm going to go here back to our previous slide set. If I take this stress value, which is uniform in this case, because now when you have axially loaded member, the stress is going to be uniform. If I take here this force divided by the cross-section area, you're going to get here uniform stress. This means if I give you here an example of a rebar, and you have the cross-section area of the rebar, and they give you the stress, and they said, let's do here integration. Integration in this case of the stress block, it means finding out the force. So in this case, I'm going to be taking this height, which is the stress value, multiplied by the cross-sectional area of the rebar, and in this case, I will develop the value of the tension force by doing sigma times A is going to be equal to P, which is the tension force. So finding out the stress block volume, it means that you find out the applied force. So okay, now let's go here. If you find out the volume of this stress block, it means that you find out the tension or compression force. It depends on the sense of the stresses that you are discussing. So in this case, I'm going to be taking this triangular stress block and try to find out the volume of it, and this is going to be equal to the tension or compression force. You can see here compression force equals, here's the stress value, I'm going to call this FC, multiplied by B, the width, multiplied by C, which is H over 2, divided by 2. Why? Because you have this area of this triangular distribution. It's going to be sigma by C divided by 2, and then again multiplied by B. And this is going to be, this equation here would be applicable to both tension and compression equation. This method here, we call it, if you look here at this, is going to be the elastic analysis method, the Flexural Formula. So if I use this equation here, if I have the stress value, right? And I'm able to find out here the two forces, T and C. And in this case, I'm going to be determining this couple. I have this couple between the C and T force. And they have the distance between the two forces. How can I have it? By putting this force, either compression or tension, at the centroid of this distribution. This couple, if I take one of these two forces, multiplied by the distance, the moment arm, can give me here the applied moment. So it's kind of, when you think about it, you say, what are you after here? Because it is not clear. You start by giving me the moment, right? And then after you have the moment, you're able to find out the stress. And then after that, you find the forces. And then after you find the forces, you find out the distance between the two forces. And then again, you ended up with the moment. So what did you do? I mean, this is actually two methods. But what I'm trying to say here, if you start with the moment value, let's say of 100 units, and you go through all of this analysis, you need to end up exactly with the same 100 units of this moment. But they are actually two different methods. The first method is called elastic analysis method, and which is this one here that we are going through. And then the other method is going to be called the couple method. And the couple method is just by taking these two forces multiplied by the moment arm between the two forces. In this example, yes, go ahead, please.
Right. So these are two methods just to analyze an uncracked concrete beam.
This is correct.
Okay, thank you.
Yeah. And the other question is, do we do cracked concrete or uncracked concrete beam in our design at all in any of the buildings in actual practice? You say no. If we do any beam design, we need to add reinforcing because we ignore the tensile strength of the concrete. But in here, I'm considering here the tensile strength. And the only reason I'm doing this, just to understand the performance of concrete and to understand the importance of adding reinforcing. But in no way that I can do this in a design of an actual building. We don't do it this way. It's just academic here exercise that we're trying to understand how the concrete performs before it start to crack and before we trigger the reinforcing bars. And let it
Thanks for that clarification.
What's that?
Thank you for that clarification.
No problem. So we have this good example. And in this example, we have been asked to determine the cracking moment for this given reinforced concrete beam. And then it says here using the following methods. Now I have here two methods, the Flexural Formula and the internal couple method. So in this example, it's going to clarify this uncracked beam performance. The first diagram given to me, it shows the stress-strain relationship for the reinforcing bars. It shows here that the steel is going to start yield at 60 KSI. And it gives me the entire performance of the reinforcing bar. Also in the concrete, it says here maximum concrete strength is going to be 4,000 PSI. Now I have both of these two materials. I have the steel and the concrete. And also I've been given the concrete section. It says this beam here, rectangular section. It is 16-inch wide by 24-inch total depth, which means this is going to be H in this case, and this is going to be B. And I have here 3 number 8 as tension reinforcing with 3 inches location from the bottom, meaning the depth D is going to be equal to 24 minus 3 inches. Let's say, where is this at? I mean, have you seen this before? I'm going to say, yeah. Let's go back here. Here is D, 24 minus 3, right? And then I'm going to have this B, it's going to be the width, H total depth, and AS is going to be the total cross-sectional area. But here the question is actually about the cracking moment. And I just said a few minutes ago that reinforcing bars are not doing anything before the beam starts to crack. This means that this reinforcing bars, I can just ignore them because they're not doing anything before the concrete is going to start to crack. And if you are after the cracking moment, you shouldn't be looking at this rebars. So truth is, you can just ignore the effect of this rebars on the performance of the concrete before the cracking point, or right at the cracking point. These rebars, they're going to start to support loads once you go beyond the cracking point. All right, let's see this flexural formula method, which is the first method, right? And let's see how much the cracking moment would be. First, we need to know at what point the concrete is going to start to crack, at what stress at the bottom, at the tension side. ACI says concrete is going to crack once the tensile stress is going to be reaching 7.5 square root of F prime C. I said, okay, let me try these numbers, and I know all the code equations needs to be in PSI, not KSI. Therefore, the F prime C, it has to be in 4,000 PSI. How do I know that the concrete strength is 4,000 PSI? I say, let me go back one step from here, from this diagram. So the strength, F prime C, is going to be the maximum stress given to me in an actual test. Okay, I'm going to have here 474.3 PSI. If I'm doing an actual analysis, I wouldn't be looking at this 0.3, right? As a practicing engineer, once it comes to PSI, I'm not going to be looking at the fraction of the PSI. If this had been in KSI, I'd be looking at the fraction of the KSI. But for now, this is an academic example, so let's just keep it like this. Now, what's going to happen? When do you think the beam is going to crack? Again, once the stress is going to be reaching 474.3 PSI. And this is stress, if you remember the equation says the stress is going to be equal to the moment, applied moment, right? Divided by the sectional modulus. Now I'm looking for the cracking moment. So it's not going to be the applied moment, then it's going to be the applied moment would be equal to the same as the cracking moment. And how much is the section modulus? Section modulus, according to the equation that you can look it up in the statics and mechanics of materials, is going to be equal to BT squared divided by 6. This equation here is from statics. In that case, the width is going to be equal to 16 inch. And this T is going to be the same as our H. In concrete design, we call this H. If you remember this H, if I may go back, it's going to be the same as this H. The total depth of the concrete section is going to be here 24 inches. So it's going to be B 16 times 24 squared divided by 6. I have this number here in cubic inches. It's going to be the section modulus. Let me plug in this equation here. I'm going to put the FCR. This is where, or the stress at which the concrete is going to start to crack. And section modulus is going to be one of the section properties. It's a constant. It is not based on the material properties. It's going to be based on the dimensions of the section. I'm going to plug this here to be 1536, like in our equation here. Therefore, the cracking moment is going to be equal to 1536 multiplied by 474. Going to have this much. And you know what? This is here in inch cubed, and this is going to be in pound per square inch. So everything here is going to be in terms of pounds and inches. Therefore, the moment is going to be equal to 728.524 pound inch. So when I do the analysis, and keep this in mind, please, put a note. When you do any analysis, you do it all in PSI. But at the end, if you like to report a moment, you need to report it in kip foot. You cannot just leave it like this big number. This would be okay if you are doing wood design. When you do structural steel design or concrete design, you'd like to report the moment in kip foot units. So in this case, I'm going to be taking this number here divided by 12 to convert the inches into feet and divide by 1,000 to put it in kips instead of pounds. Therefore, the cracking moment for this example is going to be equal to 60.7 kip foot. Any questions? You're good? So, okay, let's take the same section and let's do it to the internal couple method. All right. With the internal couple method, if you look here at the stress distribution, I'm going to say top and bottom is going to be equal to 474.3 psi. The top is going to be compression and the bottom is going to be in tension. And once the beam reaches this stress value, it means the beam is going to start to crack. Now I can do my integration thing to find out the tension and compression. Tension is going to be the same as the compression. It's going to be equal to what? The stress value, the 474.3 psi. Times the width. What width? I'm going to say the width of the beam, 16 inch. Times 1/2 of the beam depth for this triangular distribution. And then divide by 2 because I have this triangle prism for concrete block to stress. I have this much, 45,532.8 pounds as in tension or compression force. It's going to be much easier when I look at it in kips. I'm going to divide this by 1,000. I'm going to say 45.53 kips is good enough. So, okay, now I have the tension compression. Let me find out the moment arm between the two forces. I know that this force is going to be at 1/3 of this triangular base. This triangular distribution, it has a base with a height of 12 inches. 1/3 of that is going to be 4 inches. So I have 4 inches top, 4 inches bottom, and the distance is going to be equal to 24 inch total depth, subtracting 8 inches. And this is exactly what you have in the equation here. 24 minus 8 is going to be 16 inches. Take this moment arm, multiply by one of these two forces, right? This is going to be like a couple. So it's going to be 45.53 times 16. And this is going to be the cracking moment. at this stress value. Again, is equal to 60.7 kPa. We're gonna go back one slide. When I did it to the Flexural formula, I was able to get 60.7. When I did it with the couple method, it was 60.7. It has to match. If there's any discrepancy, it means I have done a mistake in my analysis. There's something wrong. Questions? Any questions? You're good? We are clear why do we have two methods? Because one of them is going to be based on the Flexural formula, which is this equation here. And the other one is going to be based on actual analysis of forces. So some people would say, this makes more sense because I can visualize or understand the meaning of a force and a couple, and I have a bunch of forces, take the moment about one point and things like this. Generally speaking, this method is simpler, just easier, because I just have one equation. And in this equation here, I set the stress at the tension side to be equal to FCR. Just solve for the moment. So this equation says FCR equals M over S. So I said, okay, I have three components, three variables. S, I can solve for it because it's going to be based on the cross-section area of the beam. FCR is going to be the value that I want the beam to attain as in tension. And MCR, the cracking moment, is going to be that moment at which the stress at the bottom of the beam is going to be right at FCR. Now I understand for this given beam here, if you apply some moment to it, if you put this in the beam, right, and then you apply some moment to it, once the moment is going to be right at 60.7, the beam is going to start to crack. So what does mean by beam is going to start to crack? Cracks is going to start to grow up at the bottom. And the effective beam depth is going to start to reduce. Imagine that I don't have here any rebars. So I'm going to put the beam here. I'm going to say, okay, here's my beam. At the beginning, when I start my analysis or start loading, the neutral axis is right in the middle. Top was compression, bottom was tension. Start to apply load, and the beam is not cracking yet. The beam is good, still working with me. All of a sudden here, beam is going to start to crack at the bottom. It means that the beam is unable to take any tension. So what happens to the depth of the beam? The depth of the beam is going to start to reduce. So your beam start to be like this. I may put them on top of each other. It's going to be the effective beam depth is going to shrink. So your beam doesn't have the same depth anymore. It's just going to reduce. What happens when the beam depth reduces? Neutral axis is going to start to go up. Correct? Becomes the depth reduces. And the neutral axis is going to be right in the mid height of the beam. In the section modulus, the value of S is going to reduce. Correct? S equals B T squared divided by 6 or B H squared divided by 6. Now, H has been reduced from, let's say, 24 inch, all of a sudden now it becomes, let's say, 23 inches. Which means the cracking moment for the cracked section is going to reduce. And the beam wouldn't take any time, it's going to collapse right away. This means if there is no reinforcing and your beam is reaching to the cracking moment, the beam is going to be collapsing in a few minutes. It's not going to take any time. Unless you put some rebars. If you put some rebars at the bottom, this rebars is going to start to get triggered. Now the tension is going to start to go into these rebars. Now, if there is no rebars, there is not to take the tension, and the beam is just collapsing in no time. When the beam here, once the beam here is going to start to crack in unreinforced beam, it's going to be just collapsing. But in a case like this, now what's going to happen? It is true that this part of the beam is going to start to crack. So it's going to happen. This rebar is going to start to take the tension, which is fine, which is okay. Now the crack depth is going to start to go up. So this part of the beam, the bottom part, is going to be cracked. What's gonna be cracked? The concrete, but not the rebars. Rebars do not crack. Rebars is gonna be good in tension. So in a case like this, compression is gonna be here in the beam and the tension is gonna be in the rebars. And you continue to add loads and the beam is surviving. It's gonna be working fine as long as you're gonna be within the design limits that we did not discuss yet. So with that, we have a good understanding for how uncracked beam is gonna perform. Why do I say uncracked? Because I'm talking about before cracking. I'm addressing it here from the zero loading all the way to the cracking point. After the cracking point, it's gonna be a complete different set of equations, and this is what we're gonna be using in our design. But in here, it's gonna be just to understand the performance of uncracked concrete. And look at the slide set title, uncracked sections. I go back here. Uncracked reinforced concrete sections. It's gonna be all about the performance of unreinforced beams or reinforced beams before the cracking point. Should we go for the second example? Yes? No questions? It says here normal weight plain concrete beam, 6 inch by 12 inch, 6 by 12. In cross section, as shown in this figure, beam is simply supported on a span of 4 feet and is subjected to a mid-span concentrated load of 4,500 pounds, like 4.5 kips. And here's a beam span. This can be a very small beam, and this beam is only for test. It is not actual beam. We don't have an actual beam with a span of 4 feet. This can be nothing, right? This is just for test in the lab. It says here, assume F prime C, the concrete strength of 3,000 psi. And then I had been asked here to calculate the maximum concrete tensile stress using the internal couple method. Repeat part A with the Flexural Formula approach. Compare both of these two methods, right? So first, this beam here is supporting a point load of 4,500 pounds. Now I'd like to see if this beam is cracking or not. How can I know that this beam has reached the cracking point? My only chance is to determine the cracking moment, as we have done here in the previous example, and then compare it with the applied moment on the beam. Once you compare it, if the applied moment is lower than the cracking moment, it means the beam is not cracked yet. I'm going to take you back here to our example. In this example, this beam here is able to support 60.7 kip-foot before cracking. If my applied moment, if I take this beam section and put it in an actual beam, and the applied moment is only 50 kip-foot, this means that the beam is not cracked yet. But if I put it and then I calculate out the applied moment and turn it to be, let's say, 100 kip-foot, it means this beam is gone. I'm gonna say this beam is gone. I mean, it's cracked already, failed. So this example here, I have again, the span is gonna be 4 feet. This beam here supports 2 loads. It is true that I'm looking at this, it says here 4,500 pounds, like 1 point load, but also I have the self weight of the beam. So any beam, any structural member would support its own weight plus any external applied loads. So the self weight needs to be considered in the analysis. The moment due to the self weight, now the self weight here is going to be uniform load because the beam section is uniform. It's going to be, this moment is going to be equal to WL squared divided by 8. If you remember from statics and structural analysis, WL squared divided by 8. And due to this point load is going to be equal to PL over 4. What is L? The span. What is P? Is going to be this load. Here's the equation for the moment. PL over 4 plus W squared over 8. This PL over 4 is going to be for the external applied load, the point load. W squared divided by 8 is going to be for the self weight. How much is the self weight? You can say here's the self weight. You can say cross section area of the beam, 6 times 12 divided by 144 to have the cross section in square feet. Unit weight of concrete is 150 pounds per cubic foot. So we're going to take this cross section area, square feet, multiply by this unit weight of the concrete. So you get me here the weight as in pound per foot of the beam. So this beam, each foot of it is going to be weight 75 pounds total. So when you look here at my moment equation, it's going to be 4,500 pounds as external applied point load, applied by the length, the span is going to be 4 feet divided by 4, plus self weight W, 75 pounds per foot, times L squared divided by 8. Look at the total moment now applied on the beam. It's going to be 4,650 pound foot. I said, okay, now I have the moment applied. Look at this, maximum applied moment on the beam. Now I need to compare this moment here to the cracking moment. The cracking moment here becomes a limited state. It's going to be one of the properties of this concrete beam. Here's internal couple method. Total depth of the beam is going to be 12 inches. You're going to have some stress on the top, stress at the bottom. This stress is going to be equal to 7.5 square root of F prime C, and my F prime C in this case is going to be 3,000 psi. Location of this concentrated load, which is compression and tension, is going to be based off the integration of this stress block. It's going to be at 1/3 of this triangular stress distribution base, which means it's going to be 6 inches, 1/3 of it is going to be 2 inches. 2 inches top, 2 inches bottom, I have total of 12. It's going to be 8 inch as a moment arm between these two forces. Now the moment is going to be equal to C times Z. We call this Z, as you see here. You can call it Z, you can call it JD, like if I may take you back to one of the slides. Sometimes you call it JD, sometimes you call it Z. I'm okay with Z. Z is okay. So the moment here is going to be equal to C or T multiplied by Z, the 8 inches. Yeah, makes sense. So what happened? They have taken this applied moment. All right. Say, if I have this applied moment, I should be able to determine the compression or tension force. Yeah. It means this is going to be the applied force. This is not going to be the cracking force. Internal forces. No, this is going to be the applied internal forces. Tension compression is going to be equal to this value. How do you do it? You have the applied moment, you have the Z, the distance between the two forces. You can solve for T or C. Here we go. I understand that this T or C I can do by integration, find out the actual stress, top and bottom of the beam. Compression force or tension force is going to be equal to 1/2 of the stress on the top or bottom, multiplied by 6 inch, which is the width, multiplied by 6 inch divided by 2. And look at the width here. The width is 6 inch. Depth is 6 inch. So we can see here for the stress block distribution, triangular distribution, the force is going to be equal to the stress value times 6 inch divided by 2 multiplied by the width of 6 inches. This is exactly what we have done here in this example, in this equation. So let's say compression force is a 69.75 as an applied force. Not the force is going to be happening at the cracking. And then we check 1/2 of F top times 6 times 6. Now your F top is going to be your unknown, and for that you should be able to find out the stress on the top or the bottom, because they're going to be equal to each other, right? It's going to be 388 psi. Now, what you can do here, you can compare this number directly to the cracking stress. Look at this. This stress here is going to be the applied stress. It is not the cracking stress. How about the cracking stress? You say 7.5 square root of F prime C. 3,000 is going to be 411. So now here's the information I have. Based on this information here, the stress at the bottom and the top is going to be 388 psi. So as in tension is going to be 388 psi. The limit state, which means the cracking stress at the bottom of the beam, in order for you to call this beam cracked, your stress needs to be at least 411 psi. Therefore, this beam didn't crack yet. Does it make sense? Yeah, so this beam is not cracking yet. But I can also use the other method, the Flexural Formula method. How can I do this? You can say, you know what? The stress is going to be equal to M divided by S, and the S equals to I divided by C. So I can say, you know what? This is the same as, if you like to call it this way, F equals M divided by S. And what is S in this case? Section modulus, right? And the section modulus S is going to be equal to I divided by C. Yeah, here's I divided by C. I should be able here to find out the section modulus or the moment of inertia, BH cubed divided by 12. Here we go. And C is going to be 1/2 of the total depth, the 6 inches. And for that, I can solve for the stress based on this equation. Because I can say F equals to M divided by S. I have the M as a value, numerical value, yes, I have it. And section modulus is going to be I over C. Let me find out the stress. The stress turned to be exactly 388. So both of these two methods will give you exactly the same stress value in tension. Now you compare one of these two values, which, I mean, they are the same, compare it with the cracking stress. If the applied stress or the actual stress on the beam is going to be lower than the cracking stress, it means the beam is not cracking yet. If this value here is going to be higher than 411, then we say the beam has already cracked. It failed. It's not working anymore. Are we good? Yep. All right. Not all beams are simple and rectangular in shape, like this beam, you know, like this beam here, like this beam here. Some beams are like T-shaped. We call this T-beam. Neutral axis will never be in the middle. It's going to be shifted up. And the moment of inertia, we have a way of calculating here the moment of inertia for a T-section like this. And also we have section models for the top and the bottom. And if you like to learn more about this, go back to statics and mechanics of materials, understand how to find out the moment of inertia for a T-section. If I may go here back to one of the slides that has a very similar beam like this, like a T-section. And in here, you're going to see all the equations you need to find out the stresses top and bottom for a T-section. So when you have a rectangular section, we say it's going to be equals to M divided by S. And in that case, for rectangular sections, S top and bottom would be the same. Now, when you have T-section, S top and S bottom would be different. Why? Because this distance here from the neutral axis to the top fibers, like this distance here, and again from the neutral axis to the tension bottom fibers. So you're going to have two different values. This is why S top and S bottom is going to be different. Moment of inertia is going to be the same for top and bottom. But because the difference in this Y top, this is going to be here Y top and Y bottom. When you take here I divided by this Y bottom or Y top, you're going to have two different S values. In the rectangular sections, I just have the term C. C is going to be 1/2 of the depth. You see the C? It's going to be here 12 inch and 12 inch in this case. Why? Because you have a rectangular section. Now let's move here to our example. So we'll assume that you're able to find out the moment of inertia for this T section. And you should be able to find out the stresses top and bottom. This is here a simply supported beam and the tension is going to be at the bottom. So it says here for this T-shaped unreinforced concrete beam, which is only for academic exploration. This is just for exercise and to understand the performance. The strength of the concrete is going to be 4,000 psi. We call this positive moment. Why positive moment? It means tension at the bottom, pressure on the top. use the internal couple method and check using the Flexural Formula. So it's gonna be very common that someone's gonna be asking, say, do a check if this beam has cracked or not, or determine the cracking moment using one of these two methods. So, all right, good. I should be able to find out here the stress distribution and the moment of inertia and the section modulus top and bottom. Here's how you find out the neutral axis location. This from statics. And then after that, we say, when the stress at the bottom is going to be reaching the 474 psi, concrete is going to start to crack. And in this case, we say, here's a cracking moment. Let's calculate out. Okay, how about the stress on the top? In the past, when we had this rectangular section, we said the stress on the top and bottom is going to be the same. But in here, can they be the same? The stress at top and bottom would be the same if neutral axis had been right in the mid-height. But because here this neutral axis shifted up, it means the distance, which we quote here y bottom, from the bottom fiber to neutral axis is going to be greater than the distance from neutral axis to the top fibers. If the stress here is at 474 psi, the stresses here is going to be lower. How can I find out the stress on the top? You see, this is going to be simple because I have here two similar triangles. So I can say stress at the bottom divided by this y bottom, the 15.33, is going to be equal to the stress on the top divided by 24 inch subtracting 15.33. Meaning this distance here, or this distance, right? If you divide here by this distance, it's going to be equal to this stress value at the bottom divided by the stress value on the top. It's like a ratio. This is exactly what we are doing. We say here 8.67. What is 8.67? Y top. What is 15.33? Y bottom times the stress at the bottom. So I'm expecting when the stress at the bottom is going to be 474 psi, and the top compression is going to be 268. Again, where is the 8.67? It's going to be this number here. You see this? 667 plus 2 inches from the center of the flange to the top, 867. It's going to be 15.33. When the stress here is 474, the stress here is going to be 268 psi compression. Any questions on this?
Yes, quick question. So you went with the bottom stress, the 474, because that was just what you were given?
No, because this is a cracking stress. And I understand because this is going to be passive moment, I'm expecting that the moment in the tension, once it approaches 474, right? I'm going to say the beam here cracked.
I see that. Yeah, thank you.
Yeah, so I set the value of F bottom to be the same as a cracking stress. And based on this, I'm trying to find out at that point when the beam cracked, when the beam here is going to start to crack, what's going to happen at the top? When the beam cracks, the stress at the bottom is going to be 474. At the same point, the stress on the top, compression is going to be 268 psi. How would I know this? From the symmetrical triangles, by doing this ratio. As I'm saying here, you take the stress on the bottom divided by the stress on the top. It's going to be equal to this distance from the bottom fibers to neutral axis divided by the distance from the top fibers to the neutral axis. Exactly what they have done. Is it okay? Now, I need to do it by the force method, this internal force method, right? They say use internal couple method. You can have here two forces. For this triangular distribution at the bottom, I have no problem to locate this tension force because this tension force is going to be at 1/3 of this triangular stress distribution. It's going to be 1/3 of this height. 15.33 divided by 3, it's going to give you this distance here. It's going to be from here to there, right? So this is going to be 1/3, this is going to be 2/3. 2/3 of 15.33 is going to be 10.2. Right? For this triangular distribution, it is so simple. just figure out the location of this tension force. It's given at 1/3 of this base. So okay, this is good. That was simple because I have triangular distribution of stress applied on the rectangular piece of the beam, which is this piece here. All of this gonna be here in tension. My problem is gonna be in the compression force. Because now where's the location of this compression force? I understand tension is gonna be equal to compression. So if you tell me here's the tension force, I'm gonna say, yeah, it's the same as the compression force in terms of the value. But the question is, where is the location of this force? It is not applied on the rectangular section here. You have a T section. So I cannot just treat it as one force. So instead, I'm gonna split this into 3 forces. I'm gonna jump this, jump here. 3 forces, like here's looking from the side of the beam. Here's the stress distribution. And if you like, this picture here would make more sense, It's gonna be the compression force. It's gonna be all triangular distribution, but over what? Over a T section. So I need to split it here into 3 forces. I'm gonna take here the bottom piece, which is this C3, right? This gonna be the bottom piece. It's gonna be on the web of the beam. It's gonna be just triangular distribution of stresses. And this force here, C3, is gonna be where? It's gonna be at 1/3 from the base of this triangular distribution of stresses, but from the top. So this distance here, if I may extend this, right? You can say the distance from this point to the point load, the C3 is gonna be equal to 1/3 of the distance from the bottom of the flange, we call this a flange, to the neutral axis. Okay. How about C1 and C2? Why do we have them? I can say because if you think here about stress distribution on this gonna be like this, right? It's gonna look like trapezoidal. Look at this. Now this becomes here trapezoidal. And for trapezoidal, it is gonna be really tough to find out the location of the centroid of this trapezoidal. So I said, why don't I split it into 2 forces? So we're gonna have this rectangular section, rectangular stress block, and triangular stress block. Here's the rectangular stress block, and here's the triangular stress block. In order for me to do this, I need to have the stress here at the bottom flange. So I'm gonna say the stress at the bottom flange, I'm gonna say, let me take you back here. I have the stress on the top, 268. If you guys remember, it's gonna be 268 PSI. The stress all the way at the bottom is gonna be what? 474 PSI. Now I need the stress at this location, which is right here. I can do the same, similar triangles. So I can say between this triangle, this big one in compression, and the small one also in compression, you say the stress at this location, at the bottom of the flange, this is what we call here the flange, and this is the web. The stress here value, which is from here to there, divided by 268, is going to be equal to this distance here, 4.67 divided by 8.67. Are you guys following me? I have here 2 similar triangles.
Yes.
Here's one, and here's a second. Let me remove this. Here's a second triangle. So I have this red triangle, and I have this blue triangle. How to find out the stress at this location? You say this is stress that I'm interested in, which is right at the bottom of the flange. Divided by 268 is going to be equal to this little distance, which is 467 divided by 8.67, which is the height of this blue triangle. 667 plus 2 inches, 1/2 of the flange. Right? Do I have an equation for this? I'm going to say, yeah. Which slide? Here's a slide. Slide number 17. Look at this equation. 467 divided by 1533. Multiply by 474. Now I need your help. I need someone to do this equation for me. 4.67 multiplied by 268 psi divided by 8.67. Can someone help me here with the stress value?
144.35.
Yeah, which is exactly this number. How did they do it here? Where did you get this 1533 and 474? I'm going to say, because they compared this little triangle, the red one, with this big triangle, which is okay. I mean, you can compare it with any one of these triangles. The one in tension is okay. The one in compression is okay. For me, it's just easier when I look at the top one, right? They're both on the same side, but it's okay. There's no problem at all. All right, now we have the stress at the bottom of the flange. Now let's look here at the beam from the side. Here's the flange, and here's the rest of the beam. The stress at the bottom of the flange, the stress here is going to be 144 psi. So let me put the stress value. Here is going to be 268 compression. And here is going to be 144 compression. And here is going to be 474 tension. Correct? Now, for this tension force, you're going to say, let me put this at 1/3 of the height. Yeah, 1/3 of the height. How about the tension force? How do you find it out? Said, yeah, here's the tension force. 1/2 now, this is going to become here triangular distribution, 474 times the height of this triangle, multiplied by the width of the web, divided by 2. So yeah, here we go. Have 5 inches, 1533 divided by 2 times the stress, 474 psi. Now here we go. Now we have the tension force. How about the location? We said yes, here's the location. You see this 10.22? Because at the end, I need to find out the distance, the z distance, right? You say, how about the compression force? You say compression force, oh, I need to know the stress right here, which is, if I may move forward, is going to be right here, the 144. I have here 3 forces. I have C1. C1 is going to be for this rectangular stress block. C2 is going to be for this triangular stress block. Then C3 is going to be for the bottom triangular stress block. Now I have 3 forces. If you have 3 forces, maybe you need to have 3 Z's. C1 plus C2 plus C3 need to be equal to tension force, to T. So let me write it down here. I'm going to say tension force equal to the compression force. And compression force equals to C1 plus C2 plus C3. Now, in a case like this, I'm going to say the moment equals. So I can write here the moment equation, right? Let me write it here. Moment equals C1 times Z1 plus C2 times Z2 plus C3 times Z3. So I have like 3 sub-moments, if you like. It's just going to be add them all together. Now, again, how do you find out C1 and C2 and C3? C1 is going to be for this rectangular block. The stress here is going to be 144. How do I know it? From here. And the height is going to be 4 inches. And the width, according to this block, is going to be 20 inches. So now let me see here. C1 is going to be 144 times 20 times 4. What is 4? The flange thickness. What is 20 inches is the width of the flange. How about C2 and C3? It's going to be exactly the same. I have 2 here, 2 triangles. That's why I see here 1/2, 1/2. I'm going to start with C3, just to be sure. Here's C3. The stress is going to be 144. And the height, 467. So, okay. C3, 144 and the height is 467, and the width is gonna be 5 inches times 1/2. So I'm good with this. How about C2 here? Where's the C2 coming from? You can say C2 is gonna equal the stress on the top. Now, how much is the stress on the top? Should I say here 268? I'm gonna say, let me zoom in, try to understand what's going on. The stress from here to here is 268. Let me write it down, 268. And the stress here, if you remember, this stress value is 144. Now, how do you find out this C2? C2 is actually based on the stress height. You see the stress value from here to there, meaning the stress from this point to that point. Then you figure this out. Let's say this stress value actually is equal to 268 minus 144. Does it make sense? So this height is going to be the difference between 268 and 144. How much is this? Can someone help me?
124.
So good. So this force C2 is going to be equal to 124 times the height, and this height is 4 inches, times 20 inch for the width, divided by 2. Do I have it? Do I have this equation? I'm going to say yes. It's going to be right here. 124, you see this, 123.6, like 124, times 20 inch the width, times the flange depth, 1/2. And if you add the 3 forces to each other, you're going to end up with exactly the same force that you have in tension. And you see the difference? 18.17, 18.18. It makes sense because the calculator errors. Just approximate, right? Very close, nearly the same as the tension. Also, based on this geometry, I should be able to find out Z1 and Z2 and Z3 based on the location of this force. So what do you do at the end? You come here and then you say, here's a moment. Moment is going to be equal to, this is MR1, which means C1 times Z1 plus C2 times Z2 plus C3 times C3. At the end, you add it up all together. And this moment is going to be the cracking moment. Any questions? All right. Let me tell you exactly what we covered today. We have 3 different examples. The first one, you have been given rectangular section. Concrete strength. Reinforcing bars are doing nothing. So when you see here reinforcing bars, and I'm talking about uncracked section or the cracking moment, right? Or the performance before cracking, you just disregard the reinforcing bars. And in this case here, I've been asked here to determine the cracking moment using one of these 2 methods. And we did. In the first one, we set the stress at the bottom to be equal to the cracking stress. And we use this equation. We have the section modulus, we have FCR, we were able to find out the moment. That was one method. Second method, based on the stress at the cracking, I have the values here, top and bottom. I was able to find out the forces, tension, compression. And I was able to find out the moment arm between the 2 forces. And here we go, here's the cracking moment. That was the first example. Second example, you have a given beam section. You have the span, external applied force. Here, they didn't say disregard or ignore the self-weight of the beam. So in a case like this, I need to consider the self-weight of the beam. If someone said in a problem very similar to this, ignore the self-weight of the beam, it means don't do this part. You see this part here is going to be the self-weight. I mean, this section is not needed if I say disregard. in this example, they didn't say disregard the self weight of the beam, so I have to do it, right? So what is this for and what is that for? I'm going to say this is to account for beam self weight. Oh. So this here for the beam self weight, and this section of the moment equation is going to be for the beam self weight. If you have been asked to ignore it, don't do it, please. So in this example here, you have been given again the beam, the span, and the external applied load. So what do you do here? You'd like to see if this beam is cracked or not under this given loads. So what you need to do is either to determine the cracking moment and compare it to the applied moment. This is going to be one way. Or determine the cracking stress and the applied stress and tension, which we have done it in this method. So in this example, we have the external applied moment. So we have the applied moment. And then we have the applied stress, 388 psi. We compare this number here with the cracking stress. Someone else could have taken exact same problem and solved for the cracking moment, very similar to what we have done in the first example, in example number 1. And then compare it with the applied moment. What is applied moment? Which is going to be this moment. If the cracking moment is lower than the applied moment, it means this beam has cracked. And if the cracking moment is larger than the applied moment, means you still have some weight before the beam cracks. The third example, we have a T-section. We could have created another example here, like a T-section, and use it in one of these two cases, one of these two issues. Find out the cracking moment or check if the beam has cracked or not. So what we have done here, we're just calculating for this T-section. We are just calculating here the cracking moment. That was it. Just determine the cracking moment, like the same as example number 1. Any questions before I let you go? No questions? All right. So go ahead and sign out. Type your name. The chat room.
Thank you, Professor.
Thank you. And if you have any questions, hang around.